Hello everyone, my name is Mohammadreza Asadi. The title of paper that I want to speak about is Deep Learning Based Multi-Classifier System for Crack Segmentation in Civil Structure Image. In general, we find cracks in different rock masses and man-made civil structures like pavement and concrete. Any type of discontinuities in such a structure are called as cracks. Now we want to detect these cracks. Crack identification is very important in maintenance of services of civil structures and buildings. Generally, cracks identification methods are divided in two categories. The first one is manual methods, which are used mostly in civil domain from past decades, and the other one is automatic methods, which are mainly based on automatic processes by computer vision techniques. In these new methods, the specification of cracks could be also calculated. But computer vision domain is mainly in contact with the image processing, machine learning, optics, sensor technologies, and geometry fields. In computer vision, some of methods are classic methods and some of them are based on deep learning techniques. The classic methods are mainly based on image processing. They use image processing for feature extraction in image, and then they apply machine learning technique for analyzing and processing extracted features. But in recent years, deep learning based methods have been more popular between expertise, which are a subset of machine learning techniques. Deep learning methods are built based on deep neural networks, and there are several deep neural networks models, but in semantic segmentation we use fully convolutional neural networks. In crack segmentation task, we try to detect all pixels of cracks in an image by deep convolutional neural networks, as is shown in this picture. For this purpose, we can use edge detection techniques, which can detect the edge of an object in an image. An example for the classical edge detection methods is CANI method, which is popular, but a subset of new deep learning based and convolutional methods are holistically nested networks. In this study, we have used two important approaches of these holistically nested networks, which are called head and deep crank model. Okay, here we have the architecture of head network or holistically edge detection network. This network is trained by hierarchical edge maps. The aim of this network is to detect the edges automatically. Head network is based on VGG network and has 5 layers, so it has 5 side outputs. In contrast with the normal convolutional neural networks, at the end of each layer and where the max polynomial layer appears, we have an image extracted from the layer called side output, and also a loss function corresponding to it. The side outputs of layers are then concatenated and compared with the ground truth image, so they form the loss function of every layer, and in this way they can optimize the parameters of each layer. It seems that we have 5 networks which are trained individually, and finally the combination of their results make the final output of head network. Another holistically nested network we have introduced was Deep Crack. Deep Crack network is basically an enhanced head network. In this model, we have the side output one, the side output of layer 1 as a guided filter for the final output of whole network. This guide filter can help to have better results than original head network. Indeed, as is clear from the title of Deep Crack Network, it is especially designed for crack segmentation tasks. Now we want to talk about multi-classifier system. As is shown in the title of our paper, we have used multi-classifier systems, which are combination of several different machine learning based classifiers. Multi-classifier systems obtain better results compared to a single classifier because they use the knowledge of different classifiers and they complete each other. In our proposed model, we have used two deep crack models in a parallel structure as a multi-classifier system. We have combined the outcomes of two deep crack models. We call the first subnetwork as SN1 and the second as SN2. Our main idea is that we want to use and combine two models with similar architecture but train on two different data sets. This can give us two different views of image and help us to process them for two different aspects. We have used a benchmark dataset available on the internet, which includes 537 RGB images of civil structures such as concrete cracks and pavement cracks, which I have annotated manually. We have extracted two different data sets from the benchmark datasets for our two networks. We resize each image to first we resize each image to 1560/80 by 1560/80 size, then divided into patch with size of 224 by 224, and then use them as the dataset D1, I mean the dataset for subnetwork 1. On the other hand, we have resized each original image to 224 by 224 and used them as a dataset for subnetwork 2 or D2. So we have 14,700 training data for SN1 and 300 training data for SN2. As is shown here in the picture, the left image represents data of D1 and the right one belongs to D2, which are for SN1 and SN2 respectively. Okay, as we mentioned before, the basis of our model is VGG16. We use first 13 layers of VGG16 model. Next we have side output layers, and in final part of our model we have a combination of parts for combining the outcome result of two subnetworks. For model implementation, we use some layers like batch normalization, ReLU, max pooling, softmax, and for model optimization we use Adam optimizer. If I want to talk about output of our proposed model, I can say it's obtained from outcomes of two subnetworks by means of a logical pixel-wise AND as a guided filter. In other words, as we can see in the picture, the detected cracks by SN1 are thick cracks. In contrast, the detected cracks by SN2 are thin, and also some noisy pixels are recognized as cracks. By applying a logical AND on these two detected cracks, we obtain final cracks. We evaluate our results by three metrics: precision, recall, and F score. We compared the result to other holistically nested Bayes methods like head and deep crack models. As you can see in this table, deep crack CRF has the highest score for precision. Our SN1, which thick detected cracks, has the best recall score, and finally the highest FR score belongs to our proposed model, which include both SN1 and SN2. Here we can see the results on some test images. As is clear, deep crack has improved the result compared to head model. SN1 outcomes have thick detected cracks, and for SN2 cracks are thin and noisy. Finally, in last row, the final results of our model is shown, which is obtained from an operator between the results of SN1 and SN2 and have the best results. In summary, we proposed a model including two deep crack models with similar architecture and different trained dataset. This results in better crack segmentation for civil structures in comparison with holistically nest-based methods. In addition, we applied these models on rock mass image dataset before and obtained a good result. After that, we motivated to apply it on other type of cracks, such as cracks in civil structures. In this study also, we see that this approach has good performance in crack segmentation. So this proves the high generality of our method for different types of cracks. Thanks for your attention.